Every human body is a thermodynamic system fighting the second law. Inside your cells, molecular machines are spending energy to hold your structure together against the constant pressure of entropy, repairing DNA, refolding proteins, replacing damaged tissue. The rate of that fight is not fixed. It depends on how much energy the system allocates to maintenance versus defense. And there is a single molecule that controls the allocation. Your own brain produces it. It shifts the energy budget of every cell in your body away from repair and towards survival. In a person who is chronically lonely, that molecule is elevated every hour of every day. The maintenance systems are defunded. The pattern degrades faster. Not because of disease, not because of genetics, because of physics. The molecule is cortisol. It is a steroid hormone synthesized from cholesterol in the adrenal glands, two small organs that sit on top of your kidneys. A threat is detected, real or imagined, and within minutes a relay chain fires through the brain, hypothalamus to pituitary to adrenal cortex. Cortisol floods the bloodstream. It has a half-life of roughly 60 to 90 minutes, designed to spike and clear. The system is built for urgency, not duration. What it does in the short term is extraordinary. It mobilizes glucose from the liver through a process called gluconeogenesis, converting amino acids and glycerol into blood sugar, so your muscles and brain have immediate fuel. It sharpens cognition by enhancing the sensitivity of the hippocampus to incoming information. It temporarily suppresses inflammation so you can function through minor injuries. It redirects blood flow from your digestive system to your muscles and brain. It inhibits reproductive function. You do not need to reproduce while running from a predator. It suppresses bone formation. Energy for building bone is redirected to immediate survival. In acute bursts, a 20-minute spike followed by clearance, cortisol is one of the most useful molecules in your body. The problem is what happens when the spike never ends. In a healthy person, cortisol follows a precise diurnal rhythm. It peaks in the first 30 to 45 minutes after waking, a surge called the cortisol awakening response, providing the energy to start the day. It then declines steadily through the afternoon and evening, reaching its lowest point around midnight. This rhythm is governed by the suprachiasmatic nucleus in the hypothalamus, synchronized to the light-dark cycle. It is as regular as a tide. In chronic stress and chronic loneliness, the rhythm flattens. The morning peak is blunted. The evening nadir is elevated. Cortisol does not properly spike and does not properly clear. The body sits in a chemical state of perpetual low-grade emergency, not high enough to trigger clinical alarms in most cases, but high enough to alter the chemistry of every tissue, every day, for years. In physics and engineering, this is a failure of negative feedback. The cortisol system is designed as a self-regulating loop. Cortisol binds to glucocorticoid receptors in the hypothalamus, which suppresses further release of the triggering signal. A classic negative feedback mechanism, the same principle that governs a thermostat, a voltage regulator, or any control system that maintains a set point. But chronic stress downregulates those receptors. The hypothalamus becomes less sensitive to the cortisol that is supposed to tell it to stop. The feedback loop breaks. The system that was designed to self-correct begins to drift, and without the restoring force, it stays elevated. In control theory, this is called a loss of gain in the feedback path. The result is always the same. The system overshoots its set point and cannot return. If you want to see what chronic cortisol does to a human body, all at once with nothing hidden, there is a disease that shows you. It is called Cushing's disease, caused by a tumor that forces the adrenal glands to overproduce cortisol. One-third of Cushing's patients develop type 2 diabetes. Between 50 and 81% develop major depression. They gain visceral fat around the abdomen. Their bones thin. Cortisol suppresses osteoblast activity, the cells that build bone. Their skin becomes fragile. Collagen synthesis is impaired. Their muscles waste. They age visibly and rapidly. And their brains shrink. The hippocampus, the brain structure most critical for memory and learning, is densely packed with cortisol receptors, which means it is uniquely sensitive to cortisol levels. Chronic exposure to high cortisol causes dendritic atrophy in the hippocampus. The branching connections between neurons physically retract. Neurons die. The hippocampus literally gets smaller. Brain-derived neurotrophic factor, BDNF, the protein that promotes the growth and survival of neurons, is suppressed. The brain loses its ability to form new connections and maintain existing ones. Cushing's disease is what happens when cortisol goes haywire at high doses over short periods. Chronic psychological stress, chronic loneliness is the same chemistry at lower doses over longer periods. The mechanism is identical. The timescale is different, and the damage to the hippocampus helps explain why chronic stress impairs memory, why lonely people report cognitive difficulties, and why social isolation is one of the strongest modifiable risk factors for dementia. All of that. The flattened cortisol, the shrinking hippocampus, the thinning bones is just the hormonal damage. Cortisol does something else. It triggers a chemical reaction inside your tissues, the same reaction that happens when you toast bread. And it is happening inside you right now. Cortisol's primary metabolic function is to raise blood sugar, not by a lot, not enough to trigger a diabetes diagnosis in most people, but enough to change the chemistry inside every tissue in your body. Because glucose, the sugar circulating in your blood, is not inert, it is reactive. And when there is more of it in your bloodstream for longer periods, it reacts with the proteins that hold you together. The reaction is called glycation. A glucose molecule floating in your blood collides with an amino group on a protein surface, typically a lysine residue on a collagen fiber. Collagen is the most abundant protein in the human body, roughly 30% of all your protein. It is the structural scaffold of your skin, your bones, your tendons, your blood vessels, your cartilage, your corneas, and some of it lasts a very long time. Collagen in bone turns over every 1 to 2 years. Collagen in skin lasts 10 to 15 years. Collagen in cartilage, the smooth, flexible tissue in your joints, can last over 100 years. Some of the collagen in your knee right now was manufactured when you were a child, and because it lasts so long, it is exposed to glucose for a very long time. The collision between glucose and collagen forms an unstable bond called a Schiff base. Over days, this rearranges into a more stable compound called an Amadori product, and over months or years, a series of further chemical reactions produces a class of molecules called advanced glycation end products, AGEs. Some AGEs modify a single protein, but the most damaging form permanent chemical bridges between neighboring protein molecules, crosslinks that the body has no enzyme to break. The most abundant cross-linking AGE in human collagen is glucosapine, a bridge between a lysine residue on one collagen strand and an arginine residue on another. Once formed, glucosapine is there for life. The collagen in your knee that was built when you were 6 years old is slowly being welded to itself, and your body has no tool to undo it. This is thermodynamic irreversibility at the molecular level. Your body has enzymes that can reverse many forms of chemical damage, proteases that cut misfolded proteins, glycosylases that repair damaged DNA, catalases that neutralize free radicals. But no enzyme exists that can break a glucosapine crosslink, because the activation energy required to cleave the bond exceeds what any biological catalyst can deliver at body temperature. The crosslink is the arrow of time written into your collagen, an irreversible state change that no biological process can undo. This chemistry has a name. It is the Maillard reaction. The same reaction that browns bread when you toast it, caramelizes the surface of a steak when you sear it, and turns onions golden when you cook them slowly. In cooking, the heat is external and the reaction takes minutes. In your body, the heat is 37 degrees Celsius, your body temperature, and the reaction takes years. But it is the same chemistry. Your collagen is slowly caramelizing, and the rate depends directly on how much glucose is present in the surrounding fluid. A person with chronically elevated cortisol has chronically elevated blood sugar. Higher blood sugar means more glucose molecules available to react with more protein surfaces. The Maillard reaction runs faster. The crosslinks accumulate sooner. Collagen in the skin stiffens. The skin cannot stretch and rebound, and wrinkles form earlier. Collagen in the blood vessel walls hardens. The vessels cannot absorb the pressure wave of each heartbeat, and blood pressure rises. The heart works harder. Collagen in the lens of the eye becomes opaque. Light scatters instead of passing through cleanly, and cataracts develop. Collagen in the joints loses flexibility. The smooth gliding surface roughens and cracks, and movement becomes painful. Pentosidyme, one specific glycation crosslink, increases roughly 200% in skeletal muscle collagen between age 25 and age 78 in people living normal lives. If you're 55, roughly half of that accumulation has already happened in your body. In people with chronic stress, the accumulation is faster. In people with type 2 diabetes who have clinically elevated blood sugar, it is faster still. Some researchers call type 2 diabetes a premature aging disease. The physics supports that label. Chronic stress produces the same biochemical signature at lower intensity over longer duration. But cortisol does not only accelerate the caramelization of your structural proteins, it reaches deeper than that. It reaches into your chromosomes. In 2004, a psychologist named Elissa Epel and a molecular biologist named Elizabeth Blackburn recruited 58 healthy premenopausal women at the University of California, San Francisco. 39 were primary caregivers for a child with a chronic illness, autism, cerebral palsy, serious developmental disorders. 19 were control mothers with healthy children. They drew blood, they measured the length of the telomeres, the protective caps on the ends of the chromosomes, in white blood cells. The results were stark. The women who reported the highest levels of perceived stress had telomeres equivalent to roughly a decade of additional aging, not a year, not two, 10 years. Their cells were biologically older than their chronological age by a full decade. What are telomeres, and why does this matter? Every chromosome in your body ends with a repeating DNA sequence, TTAGG, repeated roughly 2,000 times. These repeats do not code for any protein. They exist to be sacrificed. Every time a cell divides, the copying machinery cannot fully replicate the very end of the DNA strand, a consequence of how DNA polymerase works. So the telomere shortens. A few dozen base pairs lost per division. The coding DNA, the part that contains your actual genetic instructions, is protected, but the telomere shrinks. When it gets too short, the cell stops dividing. This is the Hayflick limit, the cellular expiration date. Blackburn won the Nobel Prize in 2009 for discovering the enzyme telomerase, which can add T-target GGGGG, repeats back onto the chromosome ends, rebuilding the cap, resetting the clock. In physics, this is a depletion process with measurable decay. Kinetics: each cell division removes a roughly fixed number of base pairs, between 50 and 200 per division, depending on cell type and conditions. The total telomere length at birth is known. The depletion rate per division is known. The critical threshold at which the cell stops dividing is known. This means telomere shortening is not a vague metaphor for aging. It is a countdown with a measurable rate, and anything that accelerates that rate, including chronic cortisol exposure and oxidative stress, brings the endpoint closer by years, and the number of years can be calculated. In the caregiving mothers, telomerase activity was suppressed. The enzyme that would normally rebuild the telomeres was being shut down by the stress chemistry. The correlation between years of caregiving and telomere shortening was strong and dose dependent. The longer the woman had been a caregiver, the shorter her telomeres. Every additional year of chronic stress was written into the molecular structure of her chromosomes, but the most important finding was not the damage, it was the exception. And it changes everything about what this research means. A small group of the caregiving mothers, women who had been caring for a sick child for years, had maintained their telomeres. Their DNA did not show the accelerated aging, and the difference was not genetic, it was perceptual. These women perceived their stress as a challenge rather than a threat. They had not eliminated the stress. They had changed their relationship to it, and that change was visible at the molecular level, written into the ends of their chromosomes. This means the telomere damage from stress is not mechanical. It is not automatic. It is mediated by perception, by the way the brain interprets the situation and translates that interpretation into chemical signals. The stress does not shorten your telomeres directly. The cortisol does. The oxidative stress does. And both of those are modulated by the signal the brain sends to the body. The same external circumstance, caring for a sick child, produced a decade of biological aging in one woman and no measurable damage in another. The difference was in the signal, not the event. The reach of this effect is staggering. Studies have found that exposure to violence, emotional neglect, bullying, and racism in childhood produces measurably shorter telomeres in adulthood. The stress does not wait for you to be old enough to notice it. It writes itself into your chromosome ends while you are still a child. Research by Entringer and colleagues found that maternal psychological stress during pregnancy is associated with shorter telomere length in the newborn. The baby arrives with pre-shortened telomeres, the stress having crossed the placenta as cortisol and written itself into the next generation's DNA before birth. And shortened telomeres cascade forward, cells reach their Hayflick limit sooner, become senescent sooner, begin secreting inflammatory signals sooner, and drive the aging process faster from that point on. But the molecular signature of loneliness goes even deeper than the chromosome ends. It reaches into the machinery that reads the DNA itself. In 2007, a researcher at UCLA looked at the DNA of lonely people and found that loneliness had rewritten their genetic code, not the sequence. The instructions the cells were following. Steve Cole used DNA microarrays, technology that can measure the activity of every known human gene simultaneously, to analyze the white blood cells of 14 people who were chronically lonely versus socially connected. Among more than 20,000 gene transcripts surveyed, he found 209 genes that were expressed differently, not mutated, not damaged, expressed differently, turned up or turned down, like volume controls on a mixing board. The DNA sequence was identical. The instructions had not changed. But the cell was reading different parts of those instructions, producing different proteins, building a different version of itself. The pattern was specific and consistent. In lonely people, genes involved in inflammation were turned up. Interleukin 1, interleukin 6, interleukin 8, tumor necrosis factor alpha. The immune system's alarm signals, the ones that trigger swelling, fever, tissue damage, the aggressive first response to infection, were chronically elevated. And at the same time, genes involved in antiviral defense were turned down. The interferons, the antibody-related pathways, the precise, targeted responses that protect you from viruses were suppressed. Cole called this the conserved transcriptional response to adversity, CTRA, and it was not unique to loneliness. The same pattern appeared in people living in poverty, people who had experienced early childhood trauma, people with unstable social status, people facing discrimination. Any form of chronic social threat produced the same genomic signature: inflammation up, antiviral defense down. In the language of physics, this is signal processing. The genome is the hardware. 3 billion base pairs of DNA, identical in every cell of your body. The transcription factors are the software, proteins that bind to specific DNA sequences and determine which genes are read and which are silent. And the social environment is the input signal. The CTRA is the program that runs when the input signal is threat. A different input, safety, connection, purpose, runs a different program from the same hardware. The DNA has not changed. The information being extracted from the DNA has changed. This is not metaphor. It is literally how gene expression works, the same source code, interpreted differently depending on the signal environment. And the signal that determines which program runs is whether you feel safe. The mechanism is the sympathetic nervous system, the fight or flight pathway. Chronic social threat activates the sympathetic nervous system, which releases norepinephrine, the fight or flight neurotransmitter, into the bloodstream and directly into the tissues. Norepinephrine does not just raise your heart rate and sharpen your senses. It reaches the bone marrow, where your immune cells are manufactured, and stimulates the production of a specific type of immature white blood cell, monocytes that have not fully differentiated. These immature monocytes have a distinctive gene expression profile: high activity in inflammatory genes, low activity in antiviral genes. They flood the bloodstream. The immune system is literally remodeled at the level of bone marrow output, not in response to any actual infection, but in response to the nervous system's assessment that you are in danger. At the transcription factor level, the pattern is consistent. The pro-inflammatory transcription factor, NF-kappa B, is upregulated. It is the master switch for inflammatory gene expression, turning on the production of cytokines like interleukin-6 and tumor necrosis factor alpha. At the same time, interferon response factors, the transcription factors that activate antiviral defenses, are downregulated. The cell is reading the same DNA but producing a different set of proteins. The genome has not changed. The interpretation of the genome has changed. And the interpretation is being dictated by whether you feel safe. The evolutionary logic is brutal and clear. For most of human history, if you were isolated from your group, the most likely physical threat was injury, a predator attack, a fall, a fight with a rival. Bacterial infections from wounds were the primary killer of isolated individuals. So your immune system shifts to prepare for bacterial wound defense, ramp up inflammation, which is the first line of defense against bacteria entering through broken skin, and reduce antiviral resources, which are less immediately useful when you are alone and unlikely to be in close contact with other humans who carry viruses. This is a rational survival strategy for a solitary primate on the African savanna 200,000 years ago. In the modern world, it is a catastrophe. There are no predators, there are no wounds, there is only an apartment and an immune system preparing for a saber-toothed cat that went extinct 12,000 years ago, running that preparation every single day. Chronic low-grade inflammation, sometimes called inflammaging, is now recognized as a central driver of cardiovascular disease, clinical depression, type 2 diabetes, cancer, and neurodegeneration, including Alzheimer's disease. The immune system is fighting a battle that does not exist, and the collateral damage accumulates in every tissue in the body. And the most striking finding from Cole's research is this: the CTRA is driven by the subjective perception of isolation, not the objective reality. It is not about how many people are in your social network. It is not about whether you are married or single, living alone or with others. It is about how many people you feel genuinely close to. People with large social networks but no intimate connections show the same gene expression signature as people who are physically alone. The genome does not count your contacts. It reads your sense of safety. This distinction is crucial, and it is consistent across every study. When Cole's team controlled for objective social network size, the actual number of people someone interacted with, the correlation with CTRA gene expression disappeared. When they measured subjective loneliness, the felt sense of isolation, the perception that the social world is hostile or unsupportive, the correlation was strong and reliable. You can be surrounded by people and still have the gene expression profile of an isolated individual. You can live alone and, if you feel genuinely connected to even a small number of people, show none of the inflammatory signature. The body is not responding to your social calendar. It is responding to the signal your brain sends about whether you are safe. This has been confirmed across species and experimental conditions. Macaque monkeys placed with unfamiliar cage mates, socially housed but not socially safe, show the same CTR pattern as isolated monkeys. Higher norepinephrine, more immature monocytes, inflammation up, antiviral defense down. The body does not care about proximity, it cares about connection. And the implication is profound. The solution to the biological damage of loneliness is not simply being around more people, it is being around the right people. People with whom you feel safe enough that your nervous system registers the contact as genuine. Connection heals tissue. That is not a metaphor. It has been measured. At Ohio State University, the immunologist Janice Kirkholt-Glaser conducted a series of studies over 2 decades that measured wound healing in couples. In one study, participants received small standardized skin wounds using a suction blister protocol, a device that creates a small uniform blister on the forearm, providing a controlled wound that can be measured precisely as it heals. Then the couples were asked to have either a supportive discussion or a conflict discussion with their spouse, while researchers recorded their behavior and drew blood samples at regular intervals. The couples who had hostile conflictual interactions healed a full day slower than the couples who had supportive interactions. One day from a single conversation. Their cortisol was higher. Their levels of pro-inflammatory cytokines, interleukin 6, interleukin 1 beta, tumor necrosis factor alpha, were elevated at the wound site. The hostility was not just emotionally unpleasant, it was physically impairing their tissue repair. And the effect was dose dependent. The more hostile the interaction, the slower the healing. Couples who were consistently hostile across multiple measured interactions showed even larger delays. The molecule at the center of this is oxytocin, a peptide made of just 9 amino acids synthesized in the hypothalamus and released from the posterior pituitary. It is released during physical touch, eye contact, warm social interaction, and sexual activity. And it does something simple and measurable. It reduces cortisol output and enhances immune function. In Kiekel-Glaser's studies, couples with higher oxytocin levels during their interactions showed faster wound healing and lower inflammatory markers, regardless of whether the discussion was supportive or conflictual. The oxytocin buffered the damage. In animal studies, the effect is dramatic. Hamsters subjected to restraint stress were divided into two groups, some housed alone, some housed with a companion. The isolated hamsters had higher cortisol and slower wound healing. The pair-housed hamsters, exposed to the identical stressor, had normalized cortisol and normalized wound healing. There was no measurable difference between the pair-house stressed hamsters and the unstressed controls. The social contact completely abolished the physical damage of the stress, and the mechanism was traced to oxytocin. The pair-housed animals had higher circulating levels. A 2025 randomized trial published in JAMA Psychiatry confirmed the mechanism in humans. 80 couples received standardized skin wounds, and neither oxytocin alone nor positive interactions alone improved healing. Only oxytocin combined with genuine affectionate contact produced faster healing and lower cortisol. The chemistry requires the relationship. In physics, this is a nonlinear coupled system. The output is not the sum of the individual inputs, but something qualitatively different that emerges only when both inputs are present simultaneously. Oxytocin without touch is a signal with no receiver. Touch without oxytocin is a receiver with a weak signal. Together they cross a threshold that neither can reach alone. Physical contact is not an emotional luxury. It is a biochemical intervention that measurably changes cortisol levels, immune cell function, and the rate at which your body repairs damaged tissue. And the reason it works is not sentimental, it is evolutionary. For millions of years, the presence of a trusted companion was the single most reliable indicator that your immediate physical environment was safe. Touch, warm, non-threatening physical contact, was the signal. When the signal arrives, the nervous system stands down. The cortisol drops. The inflammatory program deactivates. The repair systems re-engage. Your body is not responding to the idea of companionship. It is responding to the physical presence of another body. The warmth, the pressure, the oxytocin release, the way a thermostat responds to temperature. The input is physical. The output is physical. Everything in between is chemistry. Everything described so far, every mechanism, every pathway, converges on a single nerve. The longest cranial nerve in the human body, running from the brainstem all the way down to the gut, branching to the heart, the lungs, the liver, the spleen, and the intestines. It is called the vagus nerve, from the Latin for wandering, because it wanders through nearly every major organ in your body. The vagus nerve is the main channel of the parasympathetic nervous system, the rest and digest system, the counterbalance to the sympathetic fight or flight response. When the vagus nerve is active, your heart rate slows, your blood pressure drops, your digestion improves, cortisol production decreases, inflammatory signals are suppressed. The body shifts its resources from defense to maintenance and repair. The activity of the vagus nerve can be measured indirectly through a metric called heart rate variability, the variation in the time interval between consecutive heartbeats. A healthy heart does not beat like a metronome. It fluctuates, speeding up slightly on each inhalation and slowing down on each exhalation in a rhythm called respiratory sinus arrhythmia. This rhythm is a direct readout of vagal influence on the heart. The greater this variation, the stronger the vagal tone, and the more flexibly the body can shift between states of alertness and recovery. It is, in essence, a measure of how well your nervous system can adapt. Higher heart rate variability is one of the strongest physiological predictors of health and longevity. Lower heart rate variability is associated with chronic stress, loneliness, cardiovascular disease, depression, and all-cause mortality. It is a single number that captures the balance of your entire autonomic nervous system, the ratio of defense to repair, of emergency to maintenance, of fighting the world to rebuilding yourself. And here is what makes this relevant to everything we have discussed. Social connection directly increases vagal tone. In mammals, the neural circuits that control the muscles of the face, eye gaze, facial expression, the muscles of the middle ear that tune to the frequencies of the human voice, are anatomically linked to the vagal circuits that regulate the heart. This is called the face-heart connection. It evolved because mammals needed to rapidly assess whether another individual was safe or dangerous, and the assessment had to be reciprocal. When you look at another person's face and see warmth, when you hear a voice with the rising and falling prosody of calm speech, your brain registers safety. The vagus nerve fires, your heart rate slows, your cortisol drops. Your body shifts from defense to repair. A 2021 study found that resting parasympathetic activity is directly associated with greater antiviral gene expression in healthy adolescents and adults. The vagus nerve does not just calm you, it changes which genes are active in your immune cells. Think of it in the language of the physics of aging. Your body runs on ATP, adenosine triphosphate, the molecular fuel produced by mitochondria. You produce roughly your own body weight in ATP every single day, 40 to 70 kilograms of it, manufactured and recycled continuously. There is a finite supply at any moment and it must be allocated. That fuel can be spent on defense, immune activation, inflammatory signaling, cortisol production, muscle readiness, heightened vigilance, the production of those immature monocytes in the bone marrow. Or it can be spent on maintenance, DNA repair, protein folding, telomere maintenance, clearing senescent cells, rebuilding collagen, running the antioxidant defenses that neutralize free radicals. And here is where the physics becomes precise. The repair enzymes, the chaperone proteins, the quality control systems, they all run on ATP. They are, in the language of thermodynamics, Maxwell's demons, molecular machines that sort order from disorder, fighting entropy one correction at a time. Every misfolded protein they refold, every DNA lesion they repair, every free radical they neutralize is a small victory against the second law of thermodynamics, and they require energy to do it. Landauer's principle, from information theory, proves that erasing information and restoring order has a minimum energy cost. The demons are not free. They run on the same ATP that the defense systems demand. When the vagus nerve signals safety, more of that finite ATP budget goes to the demons. They work faster. They catch more errors. They maintain the pattern more faithfully. When the sympathetic system dominates, when the body is in chronic threat mode, as it is in chronic loneliness, the budget shifts to defense. The demons are defunded. They slow down. they miss errors. Misfolded proteins accumulate. DNA damage goes unrepaired. Collagen crosslinks are not cleared. The pattern degrades faster. Not because of any disease, not because of any external damage, because the energy that should be maintaining you is being spent preparing for a fight that never comes. This is the physics of why loneliness ages you. Not because loneliness is sad, not because it feels bad, because it redirects the energy budget of every cell in your body from maintenance to defense, and the maintenance deficit compounds over years. Now consider the scale of the effect. In 2010, Julianne Holt-Lunstad, a researcher at Brigham Young University, published one of the largest meta-analyses ever conducted on human mortality. 148 studies, over 300,000 people, asking a single question: does social connection predict whether you live or die? The answer was unambiguous. People with strong social relationships had a 50% greater likelihood of survival over the study periods compared to those without. 50%. To put that in context, quitting smoking increases survival odds by roughly the same magnitude. Regular exercise is in the same range. Social connection is not a soft psychological benefit. It is a survival factor of the same order as the most powerful medical interventions known. In 2015, Holt-Lunstad published a second meta-analysis, this one even larger, 70 studies, 3.4 million participants, focusing specifically on social isolation, loneliness, and living alone as risk factors. After controlling for age, sex, initial health status, and a range of other known risk factors, the results were social isolation increased the odds of premature death by 29%, loneliness by 26%, living alone by 32%. The risk from social isolation and loneliness after all those adjustments was comparable to the risk from grade 2 and grade 3 obesity. In 2023, the United States Surgeon General issued a formal public health advisory on the health effects of social isolation and loneliness, the same type of advisory issued for tobacco, opioids, and gun violence. The advisory stated that the mortality impact of lacking social connection is equivalent to smoking up to 15 cigarettes per day, greater than obesity, greater than physical inactivity. And the trend is worsening. Over the past 2 decades, the number of Americans who report having zero close confidants has tripled. Half of American adults reported experiencing loneliness even before the pandemic accelerated the isolation. These are not psychology statistics, they are mortality statistics, and they follow the same dose-response pattern used to quantify the lethality of radiation, toxins, or any physical exposure: higher dose, greater effect. More isolation, more mortality. The relationship is graded, consistent, and reproducible across populations. The mechanism is not emotional, it is physical, and you now know every step of it. Cortisol elevates blood sugar. Elevated blood sugar accelerates glycation. Glycation cross-links collagen. Cortisol and oxidative stress shorten telomeres. Shortened telomeres produce senescent cells. Senescent cells produce chronic inflammation. Loneliness rewrites gene expression. Inflammation up, antiviral defense down. The sympathetic nervous system diverts energy from repair to defense. Every pathway converges on the same outcome. The pattern that is, you degrades faster. But there is a question that precedes all of this. Why? Why would evolution build a body that destroys itself when isolated? Why would being alone change the chemistry of your immune cells, the length of your telomeres, the expression of your genes? Why would the absence of other people be treated at the molecular level as a threat to survival? Because for 2 million years it was. The genus Homo has existed for roughly 2 million years. Homo sapiens for roughly 300,000. For virtually all of that time, humans lived in small, tightly bonded groups of roughly 25 to 150 individuals, a range that corresponds to the social brain hypothesis proposed by Robin Dunbar, who found that primate group size correlates with the size of the neocortex. Our brains are literally sized for social life. The neural hardware that processes faces, voices, intentions, alliances, and threats occupies a disproportionate share of the human cortex because social information was, for our ancestors, survival information. A solitary human on the African savanna was a dead human. No individual could hunt large game alone, maintain vigilance against predators around the clock, care for themselves when sick or injured, keep warm through a cold night, or raise offspring to independence without others. Separation from the group was not a social inconvenience, it was a death sentence. The mortality rate for isolated individuals was so high for so long that evolution had time to wire the connection deep into our biology, deeper than conscious thought, deeper than emotion, all the way down to gene expression and immune cell production in the bone marrow. The result is that your body treats isolation as a mortal emergency. The hypothalamic pituitary adrenal axis activates, cortisol rises. The sympathetic nervous system shifts into dominance. The immune system reconfigures to prepare for the physical dangers of being alone. Bacterial infections from wounds, not viruses from social contact. Inflammatory genes go up. Antiviral genes go down. Sleep becomes lighter and more fragmented. A solitary primate cannot afford deep sleep because there is no one keeping watch. The body braces for impact on every front simultaneously. Your body cannot distinguish between being alone on the savannah and being alone in an apartment. The biochemistry is identical. The response is not a malfunction, it is not a weakness. It is an ancient survival program running exactly as designed. A program that made sense for 2 million years and became maladaptive approximately 200 years ago, when industrialization began separating humans from their ancestral social structures at a pace evolution could not match. In engineering, this is called an impedance mismatch, a system tuned to one signal environment, now operating in a fundamentally different one. The hardware has not changed, the world it was built for has. The late John Cacioppo, a neuroscientist at the University of Chicago who spent 3 decades studying the biology of loneliness, described it as a biological signal, like hunger or thirst. Hunger tells you that your body needs calories. Thirst tells you that your body needs water. Loneliness tells you that your body needs connection. The signal exists to motivate you to reconnect, the same way hunger motivates you to eat. It is not a character flaw. It is not a failure of resilience. It is a body doing exactly what it evolved to do, sounding an alarm that, for 2 million years, was almost always answered. But when the signal goes unanswered, when the loneliness persists for weeks, months, years, the emergency biology stays on. The cortisol keeps flowing. The inflammatory genes keep firing. The telomeres keep shortening. The body keeps preparing for a threat that never resolves. Everything described in this video is reversible. Not theoretically, not hopefully, measurably. The gene expression changes are not permanent. The CTRA, the conserved transcriptional response to adversity, the inflammatory up antiviral down signature that loneliness writes into your white blood cells, reverses when the social environment changes. Cole's research at UCLA has demonstrated this repeatedly. When people shift from isolation to genuine social engagement, the inflammatory genes quiet down and the antiviral genes reactivate. The genome responds to the new signal. Gene expression changes have been measured within weeks of social intervention. And what drives the reversal is not what most people expect. Cole found that the most powerful predictor of CTRA reduction is not hedonic well-being, not pleasure, not comfort, not the absence of pain. It is eudaimonic well-being, a sense of purpose and meaning in life. People who feel that their life has direction, that they are contributing to something beyond themselves, show a measurably different gene expression profile than people who are merely comfortable. The neural circuits associated with purpose and meaning, particularly the ventrostriatum, a brain region involved in seeking, wanting, discovery, and play, have direct neural connections to the brainstem areas that regulate the sympathetic threat response. When the ventral striatum is active, it suppresses threat signaling. Purpose vetoes fear at the genomic level. This finding has been replicated across cultures. In American adults, in Korean adults, in Japanese workers, it is not culturally specific, it is biological. Telomere length, cortisol rhythms, sleep architecture, every marker improves with sustained connection and purposeful activity. Telomerase, the enzyme that rebuilds your chromosome ends, reactivates within 2 months of daily meditation. 2 months. Cortisol rhythms begin normalizing within days of sustained social contact. Not months, days. The body wants to return to repair mode. It has been waiting for the signal. 5 minutes of controlled breathing. Specifically, cyclic sighing, two sharp inhales through the nose followed by a long exhale through the mouth, has been shown in a 2023 Stanford study to reduce physiological stress markers more effectively than mindfulness meditation. 10 minutes of walking measurably lowers cortisol. These are not lifestyle tips. They are physical interventions that alter the chemical environment inside every cell. Cole's intervention research points to something counterintuitive that matters enormously for anyone watching this who is lonely. The most effective interventions for lonely people are not about receiving help. They are about giving it. Intergenerational mentoring programs, where older adults mentor younger people, produce measurable CTRA improvement in the mentors. Acts of kindness towards strangers reduce inflammatory gene expression. When lonely people are repositioned, not as deficient, not as people who need to be fixed, but as contributors, as people with something to offer, their gene expression changes. The inflammatory genes quiet. The antiviral genes reactivate. Action changes the biology in ways that cognition alone does not. In his studies of lonely individuals, Cole has noted a common feature: an abiding mistrust of other people, a belief that the social world is fundamentally hostile. This mistrust is not irrational. For many lonely people, it is the product of real experiences of rejection or indifference. But the mistrust perpetuates the CTRA. The brain continues to read the social environment as threatening. The biology and the psychology form a feedback loop, each reinforcing the other. But the loop can be broken. It does not require a dramatic transformation. It requires one genuine connection, one act of contribution, one moment where the nervous system registers safety instead of threat. The physics of all of this is consistent and clear. Any input that shifts the autonomic nervous system from sympathetic dominance toward parasympathetic activation. Social connection, physical touch, exercise, meditation, purposeful activity, controlled breathing initiates a cascade of measurable changes. Cortisol drops, which lowers blood sugar, which slows the Maillard reaction, which means fewer glycation crosslinks forming in your collagen. The telomere rebuilding enzyme telomerase reactivates, adding TTAGGG repeats back onto the chromosome ends, pushing the Hayflick limit further away. The CTRA gene expression signature reverses, NF-kappa B activity decreases, interferon response factors increase, the bone marrow shifts back toward producing mature, properly differentiated monocytes. Vagal tone rises, heart rate variability increases, and the autonomic nervous system regains the flexibility it needs to shift between alertness and recovery. The ATP budget reallocates, less fuel spent on defense, more fuel available for the Maxwell's demons, the repair enzymes that hold you together against entropy. Every one of these mechanisms has been measured. Every one of them is real. And every one of them changes in response to what you do, not in years, but in days and weeks. And so this is what the physics tells you. You are a pattern, an arrangement of 7 octillion atoms held in a spectacularly improbable low entropy configuration by information, by the molecular instructions that tell each new atom where to go and what to do. That pattern is fighting the second law of thermodynamics at every moment. Inside your cells, molecular machines are copying DNA, folding proteins, pumping ions, generating energy, repairing damage, maintaining the structure that is you. These machines run on ATP. They are limited, they have a budget, and the rate at which they can maintain the pattern, the rate at which entropy erodes what you are, is not fixed. Social connection is not emotional comfort. It is a physical variable in the thermodynamic equation of your survival. Every conversation with someone who knows you, every moment of physical contact, every act of genuine kindness, given or received, every time another person sees you and you feel safe in their seeing. These are not luxuries, they are biochemical events. The cortisol drops, the telomerase rises, the inflammatory genes quiet, the vagus nerve fires, the demons, the repair enzymes, the chaperone proteins, the quality control systems that hold you together against the constant pressure of entropy, get more energy to do their work. You are made of the same atoms whether you are lonely or loved. The atoms do not know the difference, but the pattern degrades at different rates, and the variable that changes the rate is not a drug. It is not a supplement, it is not a technology, it is another person. If you are lonely right now, if you are watching this and the apartment is quiet and the phone has not rung and the days have started to feel the same, your body is not failing you, it is signaling you. It is telling you, in the language of cortisol and chromosomes, or gene expression and glycation, what it has been telling every human for 2 million years, that you need someone, that this is not weakness, that the need is wired into the physics of what you are, as fundamental as the need for food or water or oxygen, and with consequences just as real when it goes unmet. The act of connecting does not only help the person who is lonely, it changes the gene expression of the person who reaches out. Kindness is not a one-way transaction. It is a mutual biochemical event. Both bodies change. Both patterns are maintained a little longer. The rate at which entropy claims the pattern that is you depends in measurable physical molecular ways on whether you are alone or together. That is not sentiment. That is physics.